if you have two vectors, u and v, that have some sort of orientation like this, and the angle between them, you can find the cosine of the angle between them by finding the dot product divided by the product of the magnitudes. And really, this just stems from the fact that one way of calculating u dot v is by finding the magnitudes multiplied together times the cosine of the angle between them. So these are the same formula, really. They just are written different ways. And then I suppose thirdly, if you want to, you can say, then we can actually find theta as theta equal to the inverse cosine of u dot v over the magnitude of u times the magnitude of v. Or as someone mentioned last time, much cooler to say arc cosine than inverse cosine. It just sounds cool. I mean, it doesn't really matter though. So, not that page. One thing we sometimes like to do with vectors is talk about their projection onto other vectors. So let's say we had something that looked like this. So here's a vector u, and here's a vector v. And we want to project u onto v. So all we're going to do is we're going to drop a perpendicular from u onto v. This part here, which let's get some red pens action going on. So this vector here that I'm trying to draw in red, see how well it comes out. This vector is the projection of u onto v. And this vector here, I'll do in green, is the orthogonal complement of u onto v. And just from the get-go, what I want to point out is that you can think of u as its projection onto v plus its orthogonal complement onto v. So what do we do? How do we calculate these things? Well, let's talk about the projection of u first. To find the projection of u onto v, which always feels like a mouthful to say, we need two things. We need its magnitude. So I should really say this is true for any vector, right? If you're trying to find a vector, one way to always identify it, thank you, is to find its magnitude and its direction. So we need magnitude and we need direction. Well, let's use some trigonometry. That angle there, we can find cosine of it. So cosine of theta is equal to, so we're going to call this length here, which is the adjacent side. The magnitude, that's called the, what's the word? Like the component, yeah, the component of u in the v direction. So it's a weird name, I think, but the magnitude of the projection of u in the v direction is called the component of u in the v direction. I don't love this notation personally, but it is mostly standard, I would say. So cosine of theta is going to be this adjacent side, which is the component of u in the v direction, divided by the magnitude of this vector here. Usual trick, adjacent or hypotenuse. And then we can do some stuff. So we're going to say, well, we can get that the component of u in the v direction is equal to the magnitude of u times cosine theta. And I'm going to employ a trick that actually I feel like comes up kind of often in this section. This right-hand side here almost looks like something we know. It almost looks like the dot product over here. All we need is to multiply it by the magnitude of v. And so that's what we're going to do. We're going to multiply both sides by the magnitude of v. And it's a really it's a common trick, I feel like, that people use all the time. So we're going to say that the magnitude of v times the component of u in the v direction is equal to the magnitude of v times the magnitude of u times cosine theta. In other words, u dot v. And so then the component of u in the v direction can be calculated as u dot v divided by the magnitude of v. Welcome, thank you. Great, so there's the length of this vector. So this is the magnitude of the projection of u in the v direction. And then the direction is actually really easy. What direction is this vector pointing in? Well, it's pointing in the same direction as v. So what we're going to do is we're going to take this length and multiply it by the direction. But we have to remember that when you want to multiply by a direction vector, you want to multiply by a direction vector of length 1. So we're going to say, oh, the direction that we want is v divided by the magnitude of v. Of course, I've run out of room at a critical juncture here. So we'll go up over here and say, okay, so put this all together. And what we can say is, well, then the projection of u in the v direction is this direction times this magnitude. So our projection of u in the v direction is equal to this direction times this magnitude. Okay, so putting all the scalar parts together, that's u dot v divided by the magnitude of v times the vector v divided by the magnitude of v. Or as people often write it, u dot v over the magnitude of v squared times the vector v. It's kind of gross, but it is what it is. What's that?
That's for the projection.
That's for the projection. So that is yeah, that's there's no other better way to say it. That is the projection of u onto v. So that's, in other words, how much of u is in the v direction. I suppose you could actually call it, I guess, the component part is the how much part, and then the projection is actually the vector that is in that same direction. The other thing, the orthogonal complement after you have the projection is really, really easy. So after you have the projection, the orthogonal complement of u, well, if the projection of u plus the orthogonal complement of u is equal to u, then the orthogonal complement is just u minus the projection. So you almost never calculate this on its own. You just calculate the projection first and then say, oh, the orthogonal complement is u minus the projection. Oh, sorry, you want to see the things, maybe. I would say I've probably memorized this formula when I was a student, but it's also something, if I forgot it, I would draw a picture real quick. Like, okay, well, I know I want this part down here. I can do some quick trig and figure out what I want. Okay, let's do a couple actual examples with numbers. Again, please, if you have questions, don't stop. Don't hesitate to actually don't stop me. Please stop me if you have questions. So let's say we have the following two vectors. U is equal to I plus 3j. V is equal to 5I plus 2j. And we're going to find all the things. So first, let's draw it just so we can get a good idea of what's going on here. So I plus 3j is over 1 and up 3. So there's my U. And V is over 5 and up 2. Okay, 1, 2, 3, 5, up 2, about right there. About right there. All right, so if we want to find, first let's find the component of U in the V direction. And I'm going to draw it still. So really what I'm trying to find here is, if I drop this perpendicular, right, I'm just finding the length of this part right here. Okay, well, we found it before. it's going to be u dot v divided by the magnitude of v. I'll be perfectly honest, this is not the formula I usually remember. The formula I really remember is the whole projection formula, that it's u dot v over the magnitude of v squared times the vector v. But this is also fine. So this is going to equal, so u dot v is going to be 1 times 5 plus 3 times 2 over the magnitude of v, which is the square root of 5 squared plus 2 squared. We're going to get 5 plus 6, which is 11, over the square root of 29. So that's how long the projection of u is going to be. And then the actual projection of u in the v direction, you could either take this and say it's going to be the component of u in the v direction multiplied by v over the magnitude of v, which is going to give us 11 over root 29 times the vector v, which is 5i plus 2j over, again, the magnitude of v, which is the square root of 29. And then simplify a little bit. I guess I would probably, would I distribute the 11? I don't know. Yeah, probably. 11 times 5 is 55i. 11 times 2 is 22j over 29. Or writing it as components, 55 29's I plus 22 29's j. Which seems reasonable, right? We're going over about 55 29. So that's a little more than 2, or a little less than 2, sorry. And up 22 29 is a little less than 1. Yeah, that seems like what we have drawn closely. And then we could find the orthogonal projection of u onto v, or I should say the orthogonal complement, sorry. We're finding this part here. That's just going to be u minus what we just found, which is going to be, okay, u is I plus 3j minus this thing over here, 55 29's I plus 22 29's j. So we're going to get, let's get a common denominator. So this is going to be 29 29's minus 55 29's I. And then 3 times 29 is, 3 times 30 is 90. So 3 times 29 should be 3 less, which is 87. So we're going to have 87 minus 22 29's j. Or let's see, 6, 26, negative 26, 29's I. 87 minus 22 is 65. And again, seems reasonable, right? It looks like from there to there, we're definitely going left and up. So it definitely seems like we've got the right vector. Why would you care about this? Well, one way we might care about this would be the following. We want to find the distance from the point 1, 3 to the line y equal to 2/5 x. So let's take a look at that. So notably, I picked points at what we have. This line y equals 2/5 x is the line that this vector is in, right? I've gone over 5 and up 2. This line, you're going over 5 and up 2. There's my y equals 2/5 x. And here's my point 1, 3. So I want to find the distance, right? I'm just trying to find this perpendicular distance there, which is exactly the magnitude of my orthogonal complement. Right? If I'm trying to find the distance between a point and a line, I'm trying to find the shortest distance. And so what you can do is find the projection, then find the orthogonal complement, and find the length of that orthogonal complement. So our distance here is going to be, well, it's going to be the magnitude of this orthogonal complement, so the magnitude of this vector. Sorry, I see, yeah, no, that's right. Which is going to be the square root of negative 26 over 29 squared plus 65 over 29 squared, which I don't think we should simplify, but I will point out if you have something like this, there is one thing you can do to make it a little bit less ugly. And that's going to be, well, I know the denominator is going to be 29 squared, and the square root of 29 squared is 29. So I can rewrite this as negative 26 squared plus 65 squared, and then it's all divided by, because the square root of the 29 squared would just be 29. And that's some number that's large-ish, at least in the square root there. Just got really out of the, I'm like, what's going on over there? It's the air purifier. So questions about any of this? Yeah.
Orthogonal view in the direction of that was our direction.
So let me back up. So before we found, so the orthogonal complement of u in the direction of v is this vector here. And this vector here is the projection of u in the v direction. And so then I was asking, why might we care about the orthogonal complement? And I was trying to give an example. Well, we could say, I want to find the distance between this point, 1, 3, which is the end of the vector u, 1, 3, and this line y equals 2 fifths x, which is the line that this vector would lie in. And I said, oh, well, we could find this distance, d, by just finding the magnitude of this vector. There's a lot of kind of, in this section, a lot of weird like distance formula kind of things that just feel, I don't want to say out of place, but they just feel kind of like we've done all this stuff with series and sequences, and now we're like totally changing here and doing three-dimensional graphing and finding distances between lines and planes and points, and it feels a little disjointed, but it's kind of what we got. So we're going to go with it because we don't have much of a choice. So a couple other things about the dot product. One really good thing to know, well, in fact, one way to think about the dot product, first of all, is that if you're, let's hear that, like the really high pitched noise. It's supposed to go away as you get older, but it hasn't for me. Maybe I'm just hearing things though, that could be it too. So again, u dot v is the magnitude of u times the magnitude of v times cosine of the angle between them. And essentially what this gives you is it gives the magnitude of the product of the parts of u and v in the same direction. That's essentially what we're getting there. So however much of u and v are in the same direction, we're taking those parts together and multiplying them. It's kind of weird. It's kind of a weird interpretation of it, but it is an accurate interpretation of it. What's interesting is one useful application is it makes it really, really easy to tell if vectors are perpendicular or not. One useful application is that we can easily tell if u and v are perpendicular. If their dot product is 0. This only happens, so u is perpendicular to v if and only if. So I don't know if you guys have ever seen this before. If and only if, people sometimes get lazy and write an if with two f's. This means if and only if, meaning if one is true, the other one's true. And if the other one's true, then the first one's true. It's a, oh gosh, what's the word? It's a double implication. Each one implies the other one. So if you know one's true, the other one has to be true. If you know one's false, the other one has to be false. So this is true if and only if u dot v is equal to 0. Because none of each vector is in, like each vector, there's no portion of it in the direction of the other one. So the amount of magnitude that each one has in the other one's direction is 0. And so if you multiply them together, you get 0. An example. So here are two vectors. That are definitely perpendicular to each other. If we call this one U and this one V, we can see that U dot V is equal to 12 minus 12, which is 0. And we could also draw them. If I go over 3 and up 4, there's U. If I go back 4 and up 3, there's my V. Oh yeah, those look pretty perpendicular. But what's nice is you can do this in 3 dimensions. So you don't have to be stuck in just 2 dimensions, right? We can, for example, find a vector perpendicular to U equal to 5i minus 2j plus 3k. Now, I mean, technically in 2 dimensions, this is also true. In 2 dimensions, there are an actual infinite number of vectors that are perpendicular to this one, right? You could multiply this by any amount, this by any amount, but they all kind of go in the same direction in 2 dimensions. In 3 dimensions, if you're given one vector, hopefully you guys can see this on the Zoom. If you're given one vector, my pen, could this be a little here? Let's use this instead. Any vector in this plane is perpendicular to it. And there's an infinite number of vectors in this plane. So in 3 dimensions, if you're trying to find a vector that's perpendicular to another vector, you got a lot of choices. An infinite number. Like, for example, one vector that would be perpendicular to this one would be, I don't know, 6i. Now I'm like trying to think, 6, sure, plus 30j plus 0k. Right, if we dot those together, you get, oh, sorry, not, I forgot the 10 there, sorry, apologies. Right, 30, yeah, 10k, there we go. Dotting together, 5 times 6 is 30, negative 2 times 30 is negative 60, 3 times 7 is 30, and 30 plus negative 60 plus 30 is equal to 0. So here we're definitely getting U dot V is 0. But that's not the only choice, right? We could pick another V. V2 could be 4i minus 5j minus 10k. And our dot product is going to be 20 plus 10 minus 30. Also 0. There are lots and lots and lots, really infinite number of choices. So that is one of the useful things about dot products. And you can certainly find a vector that's perpendicular to another one using the dot product. Well, let's move on from the dot product and finally talk about the other way of multiplying vectors together, the cross product. Some people call it the cross vector product. I've never really heard of that before until I was reading the book the other day. So here is one way of calculating it that is almost never the way we're going to calculate it. So just like we don't typically calculate the dot product as U, the magnitude of U times the magnitude of V times cosine of the angle between them, we typically don't calculate the cross product in the following way. So you can think of U cross V as the magnitude of U times the magnitude of V times sine of the angle between them times the vector n, where n is a unit vector, meaning length 1, that is perpendicular to both U and V. And so technically there are 2 vectors that are perpendicular to U and V. I should say there are 2 unit vectors that are perpendicular to U and V. So if I give you, again, sorry for the, I guess I can draw things. So if I give you vectors in a plane, maybe U going this way and V going this way, which they're not meant to necessarily be perpendicular to each other. There are 2 unit vectors that are perpendicular to both of those. The one pointing up and the one pointing down. So which one should we pick? The one that is pointing in the direction determined by the right-hand rule. So in this particular one, if I'm doing U cross V, I point in the direction of U. I'm sorry, my hand is too big for this. Sorry, I point in the direction of U, I curl towards V, and then my thumb points in the direction of the correct vector. If I was doing V cross U, it would go the other way around, right? Because I put my hand in the direction of V, I'd curl towards U, and my thumb would point downwards. And again, I should have said my right hand, right? That's why it's called the right hand rule, because you put your right hand in the direction of the first vector, you curl towards the second vector, and your thumb points in the direction that it's supposed to, that your product is in. It's worth noting, just because you can see it right here, U cross V and V cross U are not going to be the same. They're going to be negatives of each other. So fun fact, V cross U is equal to the negative of U cross V. It's kind of the first product we might have really seen like that, where the order of multiplication actually does matter. If you multiply things in the opposite order, you get different things. When you take 22A, if you take 22A, you will definitely see that is also true when you multiply matrices together, is that the order of multiplication is vital. You get totally different results if you interchange the order you multiply things in. It's interesting. So I should finish this off here. N is a unit vector perpendicular both U and V as determined by the right-hand rule. Now, in reality, nobody calculates it this way. But for example, a couple things to know, we can find I cross J. So if you point your fingers in the I direction or the X direction, curl them towards the J direction, your thumb's going to point in the K direction. And that's going to be the magnitude of I times the magnitude of J times sine of the angle between I and J, which is 90 degrees, or pi over 2 radians, times the vector, the unit vector in the right-hand rule direction, which should be K. Magnitude of I is 1, magnitude of J is 1, sine of pi over 2 is 1, and you just get the vector K. So similar things are true. I cross J is equal to K, J cross K is equal to I, and K cross I is equal to J. And if you think about it, right, it's all right-hand ruling it all over the place. Here's I, here's J, here's K. If you go I, J, you're going to point upwards in the K direction. If you go J cross towards K, you're going to point outwards in the I direction. If you do K cross towards I, you're going to point in the J direction. And if you reverse any of them, you get the negatives. So it's also true that J cross I is negative K. K cross J is negative I, and I cross K is negative J. It's kind of interesting. So when you cross two vectors together, you get another vector, right? Very different than the dot product. When you dot two vectors together, you get just a number, a scalar. So that's why this is called the vector cross product, and the other one is called the scalar dot product, is because they're just telling you what kind of thing you get at. So we can use these to find cross products of other things. Like, for example, I want to find, well, I'm going to let U equal I plus 3J. V is going to equal 5I plus 5I plus 2J. And then we're going to find U cross V. So the way we're going to do U cross V, at least at first here, is we're literally just going to FOIL this thing out. So there are lots of rules about how cross products multiply out. Most of your usual mathy rules apply, meaning like you have a distributive property and you have an associative property. So, well, associative property might actually be true. You definitely have a distributive property, meaning we can FOIL this out. I can do I cross 5I plus, oops, sorry, pen, I cross 2J plus, I'm going to run out of room. It's all right. 3J cross 5I plus 3J cross 2J. Here's an important question. What's I cross I? Well, let's use the formula. I cross I is the magnitude of I times the magnitude of I times sine of the angle between them. What's the angle between I and I? 0. What sine of 0 degrees? 0. So when you cross a vector with itself, or more generally with a vector that's in the same direction as itself, the cross product is 0. You get a 0 vector, which is 0. So whenever you cross something with itself, something parallel to itself, you're always just going to get nothing. Kind of the opposite of dot products, right? Dot products, you have to be perpendicular, you get nothing. Cross products, they have to be perpendicular or in the same direction, you get nothing. So here, the I cross 5I is going to be 0. And the 3J cross 2J is going to be 0. So then we're going to be left with I cross 2J. Well, that's going to be 2 times I cross J. And then we're going to get 3J cross 5I, which is going to be 3 times 5 times J cross I. I cross J is K. J cross I is negative K. So we're going to get 2K minus 15K, which is negative 13K. And that is our cross product. Doesn't seem too heinous yet to have to do it this way. But wait, there's more. Let's do one more. So interestingly, you can't really calculate a cross product for vectors in dimensions higher than 3. Which is not something you worry about in this class. Like in this class, we are really sticking with the physical world, like 2 dimensions, 3 dimensions. We are not doing weird 4-dimensional math. But you will in 22A talk about vectors in higher dimensions. And there is definitely an analogous dot product. You can definitely take the dot product of vectors of any size that are the same size. But you can't take a cross product of vectors that are higher dimensions because it doesn't really make sense. The whole idea here is you're taking 2 vectors, you're crossing them together, and you're getting some other vector out that's perpendicular to both of them. And that's just not really something that makes sense if you extend this to a higher dimension. So fortunately, we don't have to worry about cross products in higher dimensions. But even if your vectors are both in 3 dimensions, it can be kind of a giant pain in the butt to calculate their cross product. So let's say we have these 2 vectors. U is 2I minus 3J plus K. V is I minus 2J plus 4K. If I'm going to do their cross product, okay, so we're going to FOIL out this whole hot mess. And as you might be able to tell, it's going to have 9 pieces. Now, fortunately, we know 3 of the pieces are going to be 0. So when I start foiling this out, let's see what we get. I'm going to get 2I cross I. We know that's going to be 0, but I'm still going to write it so that we see it. And then we're going to get 2I cross negative 2J. And then we're going to get 2I cross 4K. And then, let's keep going. So then let's do this piece by piece. So then I'm going to get negative 3J cross I plus negative 3J cross negative 2J, which we know is going to be 0. And then negative 3J, cross 4K. Plus, and then finally the K one, K cross I plus K cross negative 2J. Oops, you need the cross there. Plus K cross 4K, which again, that one's going to be 0. All right, and now I've forgotten which way things go. Well, so here's the nice thing. If you're doing it this way, which we're not going to do this way, but things kind of go alphabetically, meaning I cross J gives you K. J cross K gives you I, right? You circle back around. And then K cross I gives you J. So you can kind of think of it as a loop. I cross J gives you K, J cross K gives you I, K cross I gives you J. That might actually not be terrible. So doing this, we end up getting, let's see, negative 4 I cross J, which is K, and then 2 times 4, so 8 I cross k. Oh, I cross k is the wrong direction. I cross k is going to give me negative j. And then j cross I, also the backwards direction, is going to give me negative k. So I get -3 times negative k. And then j cross k is going to give me I. So it's going to be a -12i. And then k cross I gives me j. And then k cross j gives me negative I. So I get a -2 times negative I. And then simplifying, we got -4k plus 3. I should do the i's first. Come on. Don't be ridiculous, James. I've got a -12i plus 2i. So I've got a -10i. I've got a -8j plus a j. So a -7j. And a -4k plus 3k. So a -k. Gross. There's a better way, which is great. So here's the better way. It's the determinant method. Determinant method for U cross V. So reminder, matrices. So matrices are something I imagine most of you haven't seen a whole lot, like maybe a little bit, maybe not at all. Either way, totally fine. So there's only two things you need to know about matrices for this to work. Thing one, if you have a 2x2 matrix, welcome. So if you have this matrix, A, B, C, D, and you take the determinant of it, which is what this vertical bar notation means, the determinant of this matrix is A times D minus B times C. Okay. And then if what we're going to do is we're going to take the determinant of a 3x3 matrix, which is going to be the following 3x3 matrix. So if I want to find U cross V, what I'm going to do in my 3x3 matrix that I'm going to take the determinant of, in the first row, you're going to just put the components I, J, and K. In the second row, you're going to put the coefficients of U. So I'm still using the same U and V. So my U is going to be, the coefficients of U are 2, -3, 1. And then in my third row, the coefficients of V, 1, -2, 4. So coefficients of U, coefficients of V. And then we're going to take the determinant of this. And there is a method for taking the determinant of this that's really, oh, thank you, really straightforward. You take one of the rows, and the row we're going to pick here is the first row because that's the row we want to pick. It's the easiest. It's the one that makes the most sense. So you take this first row and first column. So you essentially cross out everything in the first row and first column. Come on, pens, do your job. And so you're left with this 2x2 matrix. What did we cross out that was in the first row and first column? We crossed out the I. So the first thing we're going to get is I times the determinant of this remaining 2x2 matrix. This method is called cofactor expansion. It's not super important to know that, but again, something you definitely will see if you take linear algebra, which is math 22A. And then we're going to do that again. We're going to cross out the J and we're going to see what's left. Well, if I cross out the row and column the J is in, I'm left with J times the matrix 2, 1, 1, 4. But every other term switches signs. So you're going to get a negative there. And then finally, we're going to cross out the K and we're going to be left with the matrix 2, -3, 1, -2. So it's going to be a plus K times 2, -3, 1, -2. Totally works. You could use a different row or column if you wanted to, but this one's the nicest because you get just I times your thing and J times your thing and K times your thing. So that's the one that makes the most sense. And then we're going to calculate the determinant of each of these 2x2s in the way we just did. So this is going to be I times -3 times 4 minus 1 times -2. And we're going to get minus J times 8 minus 1. We're going to get plus K times -4 minus -3. And hopefully we get the same thing we got before. -12 plus 2 is -10i. -J times +7 is -7j. And -4 plus 3 is -1k. And look, it's the same exact vector we got there. So this is the way you should do it if you're finding a cross product, unless someone has told you some other magical way of doing it that's even better. I don't think there's a magical way of doing it that's better than this. I think this is the best way. Okay. Oh yeah, we got lots of time. Again, any questions, comments, observations? You guys doing on the Zoom? You guys have any questions? Sorry if you don't. I just want to check in. I feel like I'm doing a lot of talking, which I know is typical, but still good to check in. All right, so let's look at some questions we could ask, like find a vector that is perpendicular to the plane 2x plus 3y plus z equal to 6. And not that we have to draw a picture, but we can. So here's my usual x, y, z coordinate system. And this particular plane, when I draw a plane like this, I usually try and find all my intercepts. So if I set y and z equal to 0, I'm going to get x equal to 3. If I set x and y equal to 0, I'm going to get z equal to 6. And if I set x and z equal to 0, I'm going to get y equal to 2. So here's my plane. Or I should say, here's part of my plane, right? Because obviously it extends in each direction forever and ever and ever. And I'm trying to find the vector that's kind of pointing, I don't know if I'm thinking about that, where I'm kind of pointing, up that way, right? I'm shooting out perpendicular from the plane, which is never easy for me to draw. But let's say it's coming out at you. So there's our vector. We would really like to know what vector is perpendicular, or we have to call it n for normal to the plane. By the way, there's a lot of words for perpendicular, orthogonal, normal, all are words for perpendicular is the one I usually think of as most. Yeah.
For this one, we know that we want that direction because it starts with x and goes towards y.
Well, no, so I should say that, so my drawing might not be excellent. What I've tried to draw is a vector that's kind of pointing not just purely to the left, but going kind of left, up, and right. I just haven't drawn it very, but it's really coming out of the plane and it should be perpendicular to the plane.
Right, but I mean, as far as not choosing the one that's going.
Oh, sure. Why not the other direction? Yeah, because it was easier to draw this one. But you're right. We could. So we'll get an answer, and then we can kind of decide which one we want. We could totally multiply it by a -1 if we wanted to. But you're right. I've drawn it this way purely because it was just easier to draw. But there's no good reason to pick this one versus the other one. That's the opposite direction. Yeah. So let's think about how to do this. So here's what we're going to do. We're going to take two vectors in the plane. So here's a vector that starts at the point 0, 2, 0 and ends at the point 3, 0, 0. Let's call that vector u. Or sure. So our vector u is, so it's always your, I mean, it doesn't really matter which way we go, but I decided to go this way. It's always your end point minus your beginning point. So u is going to be 3 minus 0, I, 0 minus 2, j, and 0 minus 0, k. I'm not going to write the k part. Yeah. How did I get these points? So I got those points by finding the intercepts by setting all the other variables equal to 0. So you got the x-intercept by setting y and z equal to 0, the y-intercept by setting x and z equal to 0, and the z-intercept by setting x and y equal to 0. You're welcome. Let's also look at this vector here. So that vector, I'm starting at this point and ending at the point 0, 0, 6. So this vector, which we're going to call v, is going to be 0 minus 0, I, so no I, 0 minus 2, j, and 6 minus 0, k. Yeah, Oh, I think I missed that question earlier. Sorry. No. Yeah, I did. I missed the. Sorry, I missed the thing about the longer formula. Yeah, I would say yes to your question way back when about using the longer formula for the projection. Yeah, sorry about that. So, yeah.
Why is it minus 2j?
Because for B, for both, well, so if I think about it this way, if I go from here to here, am I going in the positive y direction or the negative y direction? Right, and the same thing from here to here.
Yeah.
Now, normally, if I hadn't drawn a picture, I would just say because of the right, we're always doing the where place you end minus the place you start. So I'm doing these coordinates minus those coordinates. 0 minus 0, 0 minus 2, 6 minus 0. Same deal here. I'm doing these coordinates minus those coordinates. Now, what I wanted to observe before we find this is if I do u cross v, so if I point in the direction of u and cross towards the direction of v using the right-hand rule, I'm going to be pointing actually in the opposite direction I've drawn this vector. That's okay. So let's go ahead but the reason we're finding u cross v is if you're trying to find a vector that's perpendicular to the plane, you're finding a vector that's the cross product of two vectors in the plane. And these are definitely two vectors that are in the plane. So u cross v, all right, I'm just going to do the usual thing. I, j, k, u is going to be 3, -2, 0. V is going to be -2, 6, sorry, -2, 0. So, oh, I put the -2 in the wrong spot. Sorry. Got a little carried away there. 0i, -2j, 6k. Lovely. Good job. Okay. So then it's going to be I times the determinant of that matrix, -2, 0, -2, 6, minus j times the determinant of, basically you're just crossing out the row and column that j is in. So it's going to be 3, 0, 0, 6 plus k times the determinant of this matrix, 3, -2, 0, -2. Let's see what we get. We get I times -12 minus 0 minus j times 18 minus 0 plus k times -6 minus 0. So check this out. Our vector is -12i minus 18j minus 6k. Now, what I want to show you all real quickly is if we factor out a common factor, just to make it a little more obvious, if I factor out the -6, I'm left with the vector 2i plus 3j plus 1k. And it is not a coincidence that the components of this vector are the coefficients of x, y, and z in your plane. That is not at all coincidental. That is always going to happen. So if someone had asked me to find a vector perpendicular to this plane and I didn't want to do all this work, I could have been like, oh, another answer could have been 2i plus 3j plus 1k. That would also be a correct, acceptable answer. And it is always the case that that is true. I'm going to say it again. In fact, let me give you another example. If I said, okay, here's my plane. My plane is something silly like 4x minus 17y plus 3z equal to 8. And I wanted to find a vector perpendicular to it. All right, well, here I go. It's 4i minus 17j plus 3k. Done. Yeah. Constant doesn't matter, but you a fair point. Like it, yeah. But if you think back to this for a second, so one way you can think about the constant is the constant was just going to shift the plane, but it's not going to like tilt it in any one direction or another. So if I add more to the constant or subtract more to the constant, really, if you want, like you could think of solving this for z and saying this is the equation z equal to 6 minus 2x minus 3y. So if I add to that constant, I'm just kind of shifting the whole surface up. Just kind of like in 2 dimensions, if you add like to your function, you're just shifting the whole curve upwards. So you're not going to change the orientation. You're not going to change the direction. But yeah, good question. Yeah.
Is there a reason why the 6 is being multiplied, like we bring the 6 out and then you get?
So this particular number here is coincidental. So yeah, fair question. This is totally a coincidence. This is not a coincidence. This is like always going to happen. Yeah. So you might wonder, and so I will admit, I used to always be like, why is that true? Like, it seems very useful, but also like, why would that happen? Well, there's a number of ways you can see it. Let's talk about 2 different ways. So let's say we actually wanted to find this vector that was perpendicular to this equation, 4x minus 17y plus 3z equal to 8. Well, one way is the easy way, what we just talked about. So method 1, here's your vector, or sorry, here's your plane, which I know I'm drawing and not the right orientation. And if I say, oh, did I pick something that was, sure, I can make that easy. So we're going to pick a point. Sorry, my brain is like, yeah. Oh, I'm kind of going backwards here. Sorry, one second. Oh no, I'm silly. I know what that is. Sorry, I know what I did. So, sorry, brain. Okay. So we're going to go the other direction. Let's stop looking at this piece of paper. So finding the vector perpendicular to the plane, super easy. You can also go backwards. You can find the plane containing a point from a vector that is perpendicular to it. So for example, I could say, I want to find a plane containing the point, what do I got here? Sure, 0 to -1. That is normal or perpendicular or orthogonal to the vector 3i minus 2j minus k. And there's a couple of different ways to imagine this. So let's talk about this first way. Here's my plane that I want to find. And there's the point that I know is in it. 0 to -1. And we're going to draw the normal vector somewhere over here. And that vector is definitely perpendicular to the plane. So one way of doing this is just by using the coefficients like we already think we can, meaning if this vector is normal to it, then the plane equation should have the coefficients 3, -2, -1. So we can say, all right, we can quote unquote steal the coefficients of our normal vector n and say, all right, well then I know that I'm going to have 3x minus 2y minus 1z equal to some constant. But then I also know it's kind of like, it's very much like, you know, doing the y equals mx plus b thing. If you know the slope and you know a point, you plug in the point and then you find the b value by calculating what it has to be. Same idea here. We know the slope, not really a slope, but same idea. And we know a point. So if I plug in that point, 3 times 0 minus 2 times 2 minus 1 times -1 is going to equal our d. And that's going to be -4 plus 1. That's going to be -3. So the equation ends up being 3x minus 2y minus z equal to -3. And this is definitely the easier way of doing it. If you're given a vector that's perpendicular to your plane and a point in your plane, you can always calculate the equation of the plane by doing this sort of thing. Now, I will say the book does do it a different way, which I do think kind of helps explain more why this always works. But again, if I was doing it, I would do it this way. So here's the other way of doing this. So take your plane again and think of your normal vector sitting exactly over the point that you're given. And then our goal So when I write this equation of the plane, I'm literally describing every point in the plane, right? Any point in the plane satisfy this equation. So just for example, one point in the plane could be -1, 0, 0. Or I could have, I don't know, I'm gonna make up something, right? I could have +1, +3, 0, right? There's lots of things that would work that would equal negative. So there's really an infinite number of points in the plane. And we're trying to describe them all. Kind of like how we're trying to describe a circle, right? It's like, oh, it's all the points that are equally distant from this one center point. So we write an equation for the distance between this point and this other point, and we set it equal to the radius. And then we solve, and then we have like an equation with x and y in it. We're gonna do the same sort of thing here, where say, well, here's my point, or here's a general point in the plane. And what do we know about this vector and this vector? Let me actually back up one second. What do you know about this vector that's in the plane and this other vector? They're perpendicular to each other. And if two vectors are perpendicular, what do we know about their dot product? So check this out. This vector, let's call it V. The vector V is x minus 0 times I plus y minus 2 times j plus z minus -1 times k. And we definitely know that n dotted with v should equal 0. But n dotted with v is, well, it's the components of n times the components of v. So there's v. Here's n again. So I'm going to have, okay, 3 times x minus 0 plus -2 times y minus 2 plus -1 times z minus -1. I'm going to write z plus 1. And that should equal 0. But look, this is the same equation as that. This is kind of like the slope intercept form, where you have the slope and you find b. This is more like point slope form, where it's y, y minus y naught equals the slope times x minus x naught. That's what we were kind of doing here. But if we multiply this out, look what we've got. We've got 3x minus 2 times y minus 2 minus 1 times z plus 1 equals 0. And if we actually multiply it all out, 3x minus 2y plus 4 minus z minus 1 equals 0. 3x minus 2y minus z plus 3 equals 0. Or that, if you prefer. So it really is the same. And it's kind of neat, right? So what we're really doing is saying, oh, every point has to be true that the vector from there to that point dotted with the normal vector has to be 0. There's no other choice because that vector is perpendicular. I always thought that was like, it just seemed like a really slick way of being like, oh yeah, this thing is actually really true. So long story, much, much shorter. If you have a vector perpendicular to a plane, we know that the coefficients of x, y, and z in that plane are the components of the vector, and vice versa. If you have the equation of the plane, you know the components of the normal vector are the coefficients of x, y, and z. Cool. Yeah, we got so much time. A couple other interesting things. If you gotta go, go. Yeah. Well, so I should say, we might want to find the cross product of two vectors in a totally different context. So we might not just be using for this. So that's why we would still use the matrix to find the cross product, because we might just want to find the cross product.
But in this situation, it always holds true.
Yes. Yeah. So a normal vector, basically, so the vector n perpendicular to the plane, let's say it's ax plus by plus cz equal to, I don't care what your constant is, can always be found by stealing the coefficients. That is, the vector n is ai plus bj plus ck. Or a multiple of it, right? You could multiply it by -6 or by +3. And that's also going to be, excuse me, perpendicular because any multiple of vectors in the same direction. Okay. Here's kind of a random formula. The area of a parallelogram. Well, we draw it out. Try and draw it so things are actually parallel. Yeah, it doesn't look super parallel, but we can pretend like it is. If I call this A, B, C, and D, well, the area of a parallelogram is just your base times your height. Very, very generally. But we can also use some of the formulas we've talked about to say this different way. So if you call that angle theta, and we call this vector here V, and this vector here U, then the area, well, again, is the base, which is the magnitude of V, times the height, which is, let's do some trigonometry. Sine of theta equals the height divided by the magnitude of the hypotenuse, right? Opposite of hypotenuse, yeah. And so then the height is equal to the magnitude of u times sine of theta. So that's going to be the magnitude of u times sine of theta. But that's exactly equal to the scalar component of the cross product. So if we look back just a little bit, we said that the cross product of two vectors was, wait a little bit, way back. We said the cross product was the magnitude of u times magnitude of v times sine of theta times this vector that has a length of 1. But if we just want to know what the length of this vector is, it's going to be that times that times that times 1. So this is just the magnitude of u cross v. So the area of a parallelogram is the magnitude of u cross v. And also interesting, the area of triangle ABC. So I look at this and just, if we look at this triangle here, well, that's definitely half the area of the parallelogram. So it's just 1/2 the magnitude of the cross product. And direction order doesn't matter, u cross v, if you cross u, because if you're taking the magnitude of it, it's going to be positive. So you don't have to worry about getting it the right way or the wrong way. And then I know there's definitely, I forget, I don't remember if any, are all of you in Tavernetti's class? Is anyone not in Tavernetti's class? Okay. There's still an interesting, so there is this type of question. No, actually it's not this question, but yeah, we should just talk about all the formulas. Some of them feel kind of like, really this, but yeah, sure. There's also, we can talk about the volume of a parallel pipette. I always thought parallel pipette was a funny name. Right, it's a name for, like a box, right? But it doesn't have to be like perpendicular all the way. It could be like a tilted kind of box, or a rectangular prism, as you might often call it. But we can draw it like this. So let's say we have the following. So we're going to take our parallelogram and we're going to give it some depth. We're going to try and draw things parallel. It turned out all right. So here's our parallel pipette. And let's call this corner A, this corner B, and this corner back here C, and this corner up here D. We're going to call this vector from A to B U. We're going to call this vector from A to C V, and we're going to call this vector from A to D W. Okay. So very generally, the volume here is the area of the base times the height. It's not too bad. And the area of the base is the thing we just talked about, right? The area of the base is the area of a parallelogram, which is going to be the magnitude of U cross V. And then what about, the height here is a little tricky. So let's think about, so the height is that thing right there. So if I want to think about the height, let's look at that angle for a second. It looks like cosine of that angle is the adjacent over the hypotenuse. So it looks like cosine of theta is the height divided by the magnitude of W. So it looks like the height is equal to the magnitude of W times cosine of theta.
Is that not like is it bent?
It's slanty. Yeah. It's not like straight up and down. Sorry.
That's fine.
I guess I had said the base was a parallelogram. I mean, it is a parallelogram, but technically the way I've drawn it, it looks more like a rectangle, which is also a parallelogram. But right, it's so the base is rectangular. This front face is kind of parallelogram-y. Are we seeing that all right? Like, we've kind of done this. You can kind of see that. So that's the kind of shape we're looking at, right? Okay, that's all right. Need more props. So look what we're going to get. Area of the base is magnitude of U cross V times the height, which is the magnitude of W times cosine theta. But look what I've got. I've got the magnitude of a vector times the magnitude of another vector times, now this is where you might have, where we're going to need to say some words, times the cosine of the angle between them. Maybe James, I don't see the angle between them. I see the angle you made up that where's U. So remember, U cross V though, right hand rule, U cross towards V sticks in the direction of your thumb. U cross V has to be perpendicular to both U and V, and this vector that's sticking straight up, that is the direction of U cross V. Right? If we're thinking about this bottom part being like the flat plane, then U cross V definitely has to be sticking either straight up or straight down. So that angle there really is what I said. I'm just not making things up. But look at this. This looks exactly like the dot product of this vector with this vector. So this is exactly the vector U cross V dotted with the vector W. And then we take its absolute value in case it's negative. It's kind of a weird formula, but it's kind of neat. Are there questions about this? Because I definitely see I see a few faces that look like James. I think they're kind of lying to me. Or at least maybe haven't explained it fully. Yeah.
Well, why is the vector W not just the straight up height?
The vector W is this diagonal part here, which I did not do a good job of labeling.
Yeah, so why isn't that just the height on its own?
Well, so if we think about just the front face of this, the height is right there. So if this is my front face, ooh, I didn't draw that well. If this is my front face, which is like totally in the plane that's like sitting towards you, then that's your height. And there's your W. So yeah, so W is definitely not the height. The angle is theta. So
What is W? Just like the area, the triangle.
W is the vector. W is this vector that starts here and ends here.
Oh,
And the length of W is the length of that side. But so theta is not this angle though. Theta is this angle here.
It's not like.
Well, it's because, so, I mean, it's because really we need the angle between the vector u cross v and the vector w, so that we get that this thing is what it actually is. But if you, so, how to say this the right way? So if I'm trying to find this height, there's two ways I could have done it. I could have, sorry. So if I think about this angle here instead, maybe that one's a little easier to see. If this is W and this is H, then cosine of my angle is the adjacent over the hypotenuse, which is the exact same thing I'm getting over here. So this and this angle and that angle are the same. There's this thing called the alternate interior angle theorem from geometry way back when, where if you have two parallel lines and you cross them like this, then a lot of angles are congruent to each other. The one I'm thinking of specifically are this angle and this angle are congruent to each other because of the alternate interior angle theorem.
So why didn't you use the bar?
Why didn't I choose this angle right here? This is not the one I want. Because if I choose that angle, I have to use sine. And I have to say, well, then, so I'm gonna call this angle like beta instead of theta. So if I look at that, then I can say, well, sine of beta is also the opposite over the hypotenuse. And so I could also say that H is equal to the magnitude of W times sine of beta. But we'd rather use theta. I mean, we'd rather use theta because it ends up giving us the nice dot product formula. You could use sine of beta instead, and then you get some terrible other cross product formula, which we don't want. This is the real answer. So we picked theta because it gives us the formula that we like.
And what happens to cosine theta?
Well, so I'll remind everybody. So recall, we know that I'm going to pick two different name. Well, sure. That if you want to find u dot v, it's equal to the magnitude of u times the magnitude of v times cosine of the angle between them. So that's actually a much better answer to your question. Why did I pick theta? Because it has to be the angle between my two vectors. And theta is the angle between the vector u cross v and the vector w. And definitely this other angle down here in red is not the angle between them. So that's a much, much more reasonable answer to your question. But also the reason we like that, so what happens with the cosine theta is it gets sucked up in this formula. I've got magnitude of my vector times magnitude of my other vector times cosine theta, and that's literally equal to the dot product of this vector with this vector. That's what's happening to the cosine theta. It's becoming. So we could do an example. Yeah, it's kind of, yeah, it's fine. We got enough time to bang on this example. So let's say we have these vectors. We have that u is equal to I minus j plus 2k, and v is equal to 3i plus 6k, and w is equal to 2i minus 2j minus 3k. And we want to find, I'm just going to make up some drawing here. Right, we want to find the volume of the parallelepiped you get if you were to draw the parallelepiped with those vectors as edges that all emanate from the same corner. Okay, so what's the volume of the parallelepiped? It's gross. So here's how I would do it. It doesn't actually matter which ones you pick to be which. You can pick u and v to be like, you can do the cross product of any two dotted with the third one. But usually we're going to say, all right, it's going to be the magnitude of, not the magnitude, sorry, the absolute value of u cross v dotted with w. So let's find U cross V first. So here's an answer to your other question from before. Here's the reason why you actually just want to calculate a cross product, because you're trying to find this thing. So U cross V, good times, it's going to be the determinant of the I, J, K, and then U goes in the first row, 2, -2, -3, V goes in the second row, 3, 0, 6. Be careful, right? It's easy to forget about the 0 there. And then we're going to get I times the determinant of this, minus J times the determinant of that, plus K times the determinant of the matrix 2, -2, 3, 0. And that's going to be I times -12 minus J times 12 minus -9 plus K times 0 minus -6. So we're getting -12I minus 21J plus 6K. Okay. Oh, interesting. Oh, I said one thing. I said U cross V, but then I looked at my vectors and my W looked a lot like a U, which is also a good reason for why do we use U, V, and W? God only knows. I accidentally used W. That's okay. I could also calculate it as the magnitude of, or the absolute value of W cross V. Except I need to dotted with U. Apologies. I was looking at the notes and I'm like, this is a very different number than you get over there. That's all right. So then we're going to take that. So there's my W cross V, and now we're going to dot it with U. So W cross V dotted with U is going to be this vector. Dotted with my U, which is I minus J plus 2K. So I should get, let's see, -12 times 1, minus 21 times -1, and then plus 6 times 2, which ends up being 21, which is the same answer as I got earlier. So good. So it doesn't matter which way you do it as long as you don't make stupid mistakes. So our answer is the absolute value of this, which is 21. You don't really need to throw those absolute values on there, but if it was negative, then you would need to make sure it came out positive, because it is a volume and it should have a positive number. All right, that is all I got. One more thing. After he says that's all I've got. The reason why you might want to do this is it's a way you can check to see if 4 points are coplanar. Because if 4 points were all on the same plane, what would the volume of the parallelepiped be? If all 4 points are in the same plane, so you've got vectors shooting out this way, that way, that way, all on the same plane, are you getting a shape that has any volume? No. So if you do this calculation and you end up getting a volume that's 0, that shows you that all 4 of your points are coplanar.